Let's dive into the dynamic world of springs, where energy is stored, released, and managed in ways that are both subtle and powerful. Springs are everywhere, from the suspension in your car to the tiny mechanisms inside a wristwatch. They are the unsung heroes that make movement possible and smooth. Alongside springs, we have belts and chains, two more essential components that keep the world of machines running. Belts quietly transfer power between shafts, while chains provide a rugged, reliable link in everything from bicycles to industrial conveyors. These components breathe life into machines, offering flexibility, movement, and adaptability. They're not just passive parts, they actively shape how machines behave, respond, and perform under different conditions. Unlike static metal blocks or rigid frames, springs compress and stretch, storing and releasing energy as needed. Belts flex and bend around pulleys, adapting to changes in direction and speed. Chains, on the other hand, link rigidly yet move fluidly, transmitting force with precision and strength. Each link works together, creating a system that's both strong and flexible. Together, these parts absorb shock, transfer power efficiently, and synchronize movements with remarkable accuracy. They're crucial for timing, safety, and performance in countless machines. But representing these ever-changing, flexible components in technical drawings is a unique challenge for engineers and designers. How do you capture something that constantly changes shape, length, or position? How do you communicate its function and behavior on a flat piece of paper or a computer screen? The answer lies in a special language of symbols, conventions, and notations developed specifically for these parts. This language allows engineers worldwide to understand and build complex machines with confidence. This guide will demystify that process. We'll break down the symbols, essential notes, and critical dimensions you need to include when specifying springs, belts, and chains in your designs. You'll learn how to specify compression springs, those that push back when squeezed, by understanding their key parameters and how they're represented in drawings. We'll also cover V-belts, which are used for smooth, quiet power transmission, and roller chains, which are built for strength and durability in demanding environments. To bring it all together, we'll walk through an assembly that uses all three components, showing how they interact and how to represent them clearly in your technical documentation. This is about building your confidence and expertise as an engineer or designer, so you can tackle any project involving these essential parts. By the end, you'll have a practical toolkit, both in your mind and on your desk, for specifying, drawing, and understanding springs, belts, and chains. You'll understand the difference between detailed drawings, which show every feature, and schematic representations, which simplify things for clarity and communication. You'll know exactly what to specify for each component, ensuring your designs are accurate, manufacturable, and easy to interpret. This is about turning confusion into expertise, transforming uncertainty into clear, actionable knowledge. So, grab your tools, clear your workspace, and get ready to learn. Whether you're a student, a professional, or just curious, this journey will sharpen your skills. Let's transform complexity into clarity and make the world of springs, belts, and chains your own. Why not just draw parts as they look? It seems intuitive to create images that mirror reality, capturing every detail and nuance. However, in the world of engineering, precision and clarity take precedence over mere appearance. Because technical drawings are about truth, they convey the essential information needed to understand and construct a part, focusing on function rather than form. Springs, belts, and chains change shape with use. Their dynamic nature means that a static image can't capture their full range of motion or potential applications. Schematic representations act as symbols, like an alphabet. They form a universal language that engineers across the globe can understand, transcending language barriers. A squiggly line for a spring tells an engineer its properties. It communicates the spring's function, material, and even its load-bearing capacity without unnecessary detail. This saves time and reduces clutter. By simplifying complex components into symbols, engineers can focus on the bigger picture, ensuring efficiency in design and production. Drawings shift from defining geometry to providing instructions. They guide the manufacturing process, detailing how each part should be made and assembled. Specify material, dimensions, and performance data. These details ensure that every component meets the necessary standards and functions as intended. Use callouts and notes to link parts to the bill of materials. This creates a seamless connection between design and production, ensuring that all necessary components are accounted for. This modular approach keeps drawings clean and organized. It allows for easy updates and modifications, adapting to changes in design or requirements. It's about clarity and communication. Clear drawings prevent misunderstandings and errors, facilitating smooth collaboration among team members. Drawings become recipes, not just pictures. They provide a step-by-step guide to assembling a product, ensuring consistency and quality in the final output. This ensures everyone understands the project. By using a common visual language, teams can work together effectively, regardless of their individual backgrounds or expertise. Springs are energy masters, found everywhere from pens to trains. They push, pull, and absorb shocks. Use simple schematic symbols in drawings. Detailed helical shapes are for clearance checks only. Include a data table with key dimensions and performance data. CAD tools simplify spring modeling. Use built-in features for accuracy. Simplified configurations keep drawings lightweight. This approach ensures clarity and efficiency. Belts are power transmission heroes, connecting rotating shafts. V-belts, flat belts, and timing belts each have unique roles. Draw belt paths, not detailed parts. Use phantom lines to show routing. Focus on location and tension dimensions. Specify exact belts with part numbers. CAD layout sketches define pulley positions. Automate belt paths for efficiency. Adjust center distances easily. This keeps mechanisms in sync. Clarity in drawings ensures smooth operation. Belts are silent, but their impact is loud. Chains are the heavy lifters, gripping where belts might slip. Roller chains, silent chains, and leaf chains each serve specific purposes. Draw sprockets accurately. Show chain paths with phantom lines. Specify chain pitch and standards in notes. Use KD patterns for detailed chain modeling. Model one link, then pattern along a path. Suppress detailed views in manufacturing drawings. Focus on routing and connections. Maintenance notes are crucial for longevity. Chains are robust, and their drawings should be precise. This ensures reliability and efficiency. Follow standards like ANSI and ISO for universal understanding. Use schematic symbols in assembly drawings. Keep details in the bill of materials or separate drawings. Include installation and maintenance information. Manufacturer catalogs are invaluable resources. Select parts from catalogs to save time. Call out part numbers in drawings. This leverages expertise and ensures reliability. Standards prevent mistakes and streamline processes. Drawings should be clear, organized, and precise. This approach benefits everyone involved. It's about effective communication and design. Let's walk through a real-world example by building a motorized rock tumbler. This project will use a combination of springs, belts, and chains to create a smooth, reliable motion. Imagine the process from start to finish as we bring together mechanical components to form a working system. The first step is to draw the main frame, the motor, pulleys, sprockets, and the barrel where the rocks will tumble. Each part must be carefully positioned to ensure everything fits together seamlessly. Use phantom lines in your engineering drawing to indicate the paths of the V-belt and roller chain. These lines help visualize how power will be transmitted from the motor to the barrel, making the design easier to understand. Next, add balloon callouts that are linked directly to the bill of materials, or BOM. This step is crucial for keeping track of every component, from the smallest screw to the largest sprocket. Be sure to specify all the belt and chain details in the BOM, including their sizes, materials, and any special features. This ensures that when it's time to assemble, you have exactly what you need. Include precise dimensions for fixed center distances between shafts and pulleys. Accurate measurements are essential for smooth operation and to prevent unnecessary wear on the components. Make a note of the spring's function in maintaining proper belt tension. The spring ensures the belt stays tight, compensating for any stretching over time and keeping the system running efficiently. For any custom mechanical parts, create separate detailed drawings. These detailed views provide exact specifications for manufacturing or 3D printing, reducing the risk of errors. All these steps together ensure clarity and completeness in your documentation. A well-documented project is much easier to build, troubleshoot, and maintain. The assembly drawing acts as a universal language, communicating the design intent and assembly process to anyone involved, from engineers to technicians. Clean, organized documentation is the backbone of any successful engineering project. It saves time, reduces confusion, and helps everyone stay on the same page. By following this approach, you ensure the machine not only looks good on paper, but also functions exactly as intended in the real world. The result is a simple, elegant mechanical system, one that's easy to understand, build, and maintain. Your engineering drawing becomes a true blueprint for success, guiding the project from concept to completion. This is how you transform an idea into reality, by carefully planning, documenting, and executing every detail. That's the power of great engineering drawings. Avoid common mistakes like over-detailing. Simplify in assembly drawings with schematic symbols. Ensure drawings communicate clearly. Include all necessary specifications. Use checklists to avoid missing key information. Reference standards for clarity and interchangeability. Include installation and maintenance notes. Avoid ambiguous language in notes. Be precise and actionable. Engineering is about precision and clarity. Elevate drawings to professional standards. This ensures effective and efficient communication. We've explored springs, belts, and chains. Their dynamic nature requires a special drawing approach. Representation should be simple, specification complete. Communicate intent, not just shape. Use schematic symbols and organized specifications. Reference standards for universal designs. Include installation notes for functionality. Mastering this improves design and communication. Consider the entire life cycle of components. This guide aims to build confidence and expertise. Learn by doing, make mistakes and improve. Keep exploring, building, and creating.